Hello there. So for today's lab, we are going to cover vision transformer, which was introduced by some researchers. The title of paper was "An image is worth 16 by 16 words," and transformers for image recognition at scale. ViT's model basically kind of like become the state of art for image classification task. The main idea behind the paper was that unlike traditional tasks that when we use convolutional neural network for image processing, and as we know, convolutional models basically do like a local embedding over the image. The idea was that instead of doing something like that, we want to have more sort of like a global representation of the image. And in order to do that, what we will do, we break down basically an image into a smaller patch, and we basically first kind of like flatten these patches that we have, and then we add some positional encoding to this flattened representation, and then we basically do a transformer encoder on those, and then we have the downstream task, which is like, the classification here. So that was the idea, and that's what we're going to basically do in this lab. However, for the lab, I'm going to perform this in two different ways. The strategy one is that when we have the image, in order to create these patches, I basically ran a convolutional layer, and because the breaking down the image into a smaller patch, that's kind of like a resemblance of if you're doing a convolution over that and getting these activation maps. So basically, what we do here, in approach one, I basically do a convolution over the image, and I get this smaller patch output of the convolution, and then we follow basically the rest of the architect. In the second approach is that we are not using the convolution. We just break down the image into a smaller patch, and we do an embedding layer to convert those basically flattened patches into some embedding representation or contextual representation. And then after that, we follow the same architect. So let's start. So there are some environmental basically imports and variables that we need to set here. But overall, basically, the idea will be that I'm going to use with the CIFAR 10 dataset. So we load the dataset here. There is this function for basically, or this model, which the job is that to do some data augmentation. So we do normalization, image resizing, random flip rotation, and adding some basically zoom to the images. So we call that data augmentation. That's going to be common across both approach that we are going to look at. So in strategy one, which we are going to use convolutional embedding. So we have this class called patch embedding. The idea of this class is that we basically want to break down an image into a certain number of patch, and then we want to have this embedding dimension. So in order to create that embedding dimension, one thing that we could think about is that one way of resemblance of an embedding vector is, let's say, if we want to have an embedding dimension of 108, that technically could be done by doing one convolutional layer with 108 filters, right? Each filter basically gives you one dimension. So together, you basically end up with 108 basically dimension. So here, in order to do that, we first, look at the image source, how many patches we want to create, and basically we get the number of patches. So we do convolutional 2D, number of filters is the embedding dimension. Kernel size becomes the number of basically this patch size, sorry. And stride basically also we leave it as patch size, and we want it to be valid padding. And after that, we have this layer that basically reshapes or flattens the output of the convolution, basically. Okay, so when you call to this basically class, it gets as an input an image. It projects the image using the convolution, and it flattens and returns the image. So if you basically initiate this class and take a sample from the CFR10 data that we have. So this is an example of a sample image. after basically we kind of like enlarge the image. They're not there by default; they're smaller. So, and then when we run the convolution, these are the output of the convolutions that we see. So as you can see, of course, we ran a convolution here, just without training, so we don't see anything meaningful at the moment. But the hope is that while we train the model, but when you do backpropagation, we learn and adjust the weights to learn better contextual representation. So the next thing here is that we want to define a class or a model called simple ViT, or vision transformer. And the way that we're going to start here is that we basically, remember in the architect was we need a positional embedding after you have the, so basically after we have this part done, the linear projection, which was done with, so this one was done with convolution, and we had this flattened layer. So then we need a positional embedding, and we need a transformer layer block, basically. So we introduced this positional embedding, and then we basically introduce a one layer of multi-head attention. We do layer normalization, and then we basically have some basically dense layer or multi-layer perceptron for the downstream task that we have. And then we, at the end, we do a number, basically dense layer with the number of classes that we make the prediction for. So data comes through, we augment the data, we patch the data using the patch embedding that we saw above. We do a positional embedding. Here we have the positional embedding. We add the positional embedding to the output of the patch embedding. And then we do an attention block, obviously multi-head attention block, multi-layer attention block. And then we do layer normalization. We basically do residual connection here. We add the data plus the output of the multi-layer perceptron. And then we do reduce mean to average, basically the result for the classification head. And then we pass that to the final output, which is converts the data to a number of classes that we do for classification. So this is a simple version of the basically vision transformer. If we run this experiment, so here I'm using AdamW as an optimizer. We basically do sparse categorical cross entropy for loss, and for metric we do a sparse categorical accuracy, a sparse top categorical accuracy. And we basically let this model to run. So I already have ran the model, and it took quite a while. So the test accuracy we achieved was 54%, and top 5 test accuracy was 94%. Which it's an okay basic performance for a small model like this. So the next strategy was that, so instead of using a convolution, we're going to follow what we saw in the paper. So that means we convert the image into smaller batch or patches size of the image itself without convolution. Then we flatten these smaller patches. We pass those through an embedding layer. Then we do the same thing like a patch and position embedding, and then basically transfer encoder and multi-layer perceptron, which for classification. So let's continue here. So let's go back. We start with here. For patches, basically, what we will do is that we just using the TensorFlow image extract patches function. It basically, you give an image and you say that what's the size, what's the stride. It does similar to convolution, basically convolving over to create those patches, but it doesn't basically, it doesn't give you the contextual representation. It just gives you the actual date, actual image patched, and compared to what we did previously, convolution, which convolves actually over the image. And then this to just reshape the function into the basically shape that we are looking for, do like a flattening. So if we run this over same image, that's what we are basically getting as an output. As you can see, you get the actual image patches basically back, not the convolution values over those. So the next step becomes the patch encoder. So the idea here was that we have this, basically, we're going to convert those into a dense representation. And then we pass those to an embedding layer to get the, some embedding representation. And the dimensions here are the same as the dimension that we have seen above. So the call function gets the patch. it basically expands the dimension of this patch to the dimension that we want, and then it passes to this projection layer, which was simply a dense layer of which converts it to like a dense representation, and then it passes that to the positional embedding, and basically add that output of that positional embedding back to the projected patches, and that becomes the encoded that we have. All right, so that basically becomes this first part of the up to this part patch plus position embedding. Now, what we want to do, we want to build this transformer encoder basically layer, and basically pass the data to that layer. So we go down here. We first create the last layer, which is the multi-layer perceptron. Here, basically, what we do, basically, depending on how many hidden units that we have, we loop through the data loops through this and goes through a dense layer, a dropout, and so on. Now, let's go to the ViT classifier or vision classifier. So basically what happens here is that we start with an input, we do data augmentation, we perform patching basically, which just breaks down the image into a smaller patch. Well, we do the patch encoder. That means we pass those patches to a dense representation and plus the encoding, like positional basically encoding. And then we basically, depending on how many transformer layers we have, this could be a multi-layer, we basically do a layer normalization. We create a multi-head attention. We pass the data there. We do an add attention output plus the encoded patch that we have. We do layer normalization, multi-layer perceptron, and again we add this two together. It's like we have this residual connection, one here, and then we have one basically here. So we loop through, depending on number of transformer layers that we have, we loop through this function. And at the end, we perform another layer normalization. We flatten the output, and then we do a dropout. We pass it to the final layer, which was the multi-layer perceptron, and then we basically do the classification layer, which is the dense layer with the number of classes as the units. So this becomes our model. I already basically have tested the model also. So we basically run an experiment with same basically cost functions, optimization, and basically metrics that we had for the previous one. This model took much longer than in compared to the previous one because of the number of transformer block that basically it happens in it. I think it took about like 4 or 5 hours, something like that, if I'm not wrong. But it did achieve a much higher test accuracy. Like the previous one was about 50%. This one gets about 70%, and test top 5 accuracy was 97%. Okay, and I think right now the state of art for this data is, I think, is like almost 100%, if I'm not wrong. So that was the idea of the ViT. So the main goal of the paper was that instead of doing the basically traditional image classification using convolution, which we do local, basically embedding over the images, we want to have more like a global embedding, or basically a global representation. Which the idea is that instead of, as we know, convolution does basically local basically sliding, and when we do the transformer or attention, basically we allow every batch to basically attend to every other batch basically across the entire image. So that becomes a global basically representation. All right, thank you.